the diagram of this beam. In this question, you're required to calculate the moment at this point, point A. Based on the previous problem, you completely know how to draw the free body diagram of this beam. You have a concentrated force here, 2 kilonewtons. You have a concentrated moment here, 3 kilonewton meter. And at this point, you have 3 reaction forces, RAY, RAX, and a moment MA. So to calculate all the components, first of all I write the equilibrium equation in x direction. Sigma fx equals to 0, and this is the positive direction. So the only horizontal force is RAX. Therefore, RAX equals to 0. Then I'm going to write the equilibrium equation in y direction with this direction marked as positive. So based on the free body diagram, I have RAY minus 2 kilonewtons equals to 0, which leads to RAY equals to 2 kilonewtons. Here is the second component. And the last equilibrium equation is sigma m at point A equals to 0 with this direction as positive. So this gives us MA minus the moment created by this force at this point, 2 times this distance, which is 4, minus the concentrated force here equals to 0, and this one gives us MA equals to 11 kilonewtons meter. So the final free body diagram of the beam is like this. The 2 kilonewton force, the 3 kilonewton meter moment. Here there is a vertical force RAY equal to 2 kilonewton and a moment of 11 kilonewtons meter. Here is question 226. In this question, you are required to calculate the reaction forces at these 2 supports. So here we have a beam with points, say, A and B. Here there is a 60 kilonewton meter moment. Here we have a concentrated force of 10 kilonewtons, and here is an evenly distributed force of 5 kilonewtons per meter. And based on these 2 supports here we have a pin support, so there is an RAY as well as RAX, and here it is a roller support, so we just have RBY. First of all, I'm going to write the equilibrium equation in the direction x. Sigma fx equals to 0, so the only horizontal force is RAX, and it is equal to 0. The next equation I have is sigma m at point A, this point, is equal to 0 with this direction as positive. So if I start from right hand side, I have RB times this distance, which is 3 plus 4 plus 3, 10, based on the question, minus this concentrated moment. It is negative because it is opposite the positive direction, so it is negative, minus 60 minus the moment created by this force, which is 10 times this distance, which is 3, and it is negative as well. And to calculate the moment created by this evenly distributed force, you may remember from the lecture that when you are going to calculate the reaction forces, you are allowed to substitute this with a concentrated force at its middle, and it is equal to 5 times this distance, which is 3. The magnitude and the distance is half of this distance, which is 1.5 meters. So the moment created by this distributed force is equal to 5 times 3 times 1.5 equals to 0. This gives us RBY equal to 11.25 kilonewtons. So we go to the last equation we have, the equilibrium equation in the direction of y. Sigma Fy equals to 0 and upwards is marked as positive. So we have RBY minus 10 minus 5 times 3, which is the distributed force, plus RAY equals to 0, which leads to RAY equals to 13.75 kilonewtons. So we have calculated all the 3 reaction components.